Hello, I'm Mark Bouwman. I'll be giving a presentation on formalizing SysML state machines in mCRL2. This is joint work with Jurre van der Wal from the University of Twente and my direct colleague here at the University of Eindhoven, Bas Luttig. I'll give a bit of context first. So this is in the context of ULinks. And ULinks is a collaborative effort of a number of European railway infrastructure managers to standardize signaling interfaces. And this paper is part of Formalisation, a collaboration between ProRail, Deutsche Bahn, University of Twente, and Eindhoven. And the main goal is to support ULinks with formal methods in three distinct ways: by formalizing the ULink standard so that the standard is completely unambiguous, to check the correctness of ULinks in the sense that it doesn't contain safety errors, and to check conformance of implementations to this ULinks standard. And the central idea of Formalisation is to take models that are developed in ULinks. So ULinks uses a model-based engineering approach and uses SysML. And our approach is to translate the SysML models to mCRL2. And then this mCRL2 model can be the heart of the formal analysis. So on the one hand, we can use the mCRL2 model for model checking using the mCRL2 toolkit. So we can check safety requirements, which are, of course, in the railways very important to verify. And on the other hand, we can use this mCRL2 model for conformance testing using a model-based testing toolkit like JTorx. And this talk and the paper are mostly about this translation from ULinks SysML to mCRL2. So ULinks SysML, to be a bit more specific, ULinks uses state machines which are common to both UML and SysML, and SysML-specific internal block diagrams to define port connections between components. So I'll explain a bit more about state machines and these internal block diagrams. So state machines, I know this picture can be a bit daunting, but I'll explain the basic ideas of state machines. So the basic ideas are states and transitions. So states like this initial state and forks and starting controller are also all as a state that the system can be in. And as you can see, these states can be nested and can have parallel regions. So the composite state booting can be simultaneously in the state starting controller and starting reactor. We have transitions between these states, and transitions may have a guard. So for example, we have a guard here, controller state is equal to booted. The transition is only fired when the guard is true. A transition may have an effect. So in this transition, the variable m is assigned the value error. And a transition may have a trigger. So for example, here we have a timeout trigger that is triggered after 20 seconds. We also have a range of pseudo-states, like initial states, fork, vertices, and so forth. I will not explain these further. You can read about them on the OMG website if you like. They will not be necessary to understand for the rest of this talk. Then ULinks adds a way of letting state machines communicate using SysML internal block diagrams. So here we have a small fragment of such an IBD where we see two output ports connected to two input ports. And these ports are referenced as variables from the perspective of state machines. So let's say this left component wants to send something on this channel from T7CD PDI version check to the receiver. Then it simply assigns to the name of this port a value, true in this case, and this will send this value across the port connection. And the receiver similarly reads from the input port by referencing it as a variable. So for example, here we use this input port as a trigger. Then a bit about mCRL2. So mCRL2 is a process algebra with a pretty extensive toolkit for state space generation, bisimulation reduction, verification of mu calculus formulas. So that's the properties language of the mCRL2 toolkit. It supports counterexample generation when a property fails to hold. And one of the main things I want to note is that it has a pretty rich data language. So in particular, you can define your own abstract data types and define operations on these data types. And this is something that we will use quite a bit in our formalization. Then on to our formalization strategy. So this slide contains most of the content of our FORTE paper. So our key strategy is to directly formalize the semantics of these state machines with port connections in mCRL2. How do we do this? Well, we define the structure of these state machines directly in mCRL2 using these custom abstract data types. So we define that a state machine has a number of states, it has a number of transitions, and so forth and so forth. A transition in turn has a trigger, it has a guard, and we can define all these things using these abstract data types. And then we generically define the behavior using these abstract data types. So we use the operations on calculating, if we have a bunch of transitions, we can use operations to calculate which ones are enabled, given a certain state that we are in at the moment. And we use a process definition, so we define a state machine process that describes generically for any state machine how that state machine behaves, what kind of steps it makes. If it takes a transition, how does it affect the dynamic behavior, the runtime status of this state machine. So this is how we generically define the semantics. And then we can instantiate this generic model with a configuration by having concrete instantiations of these abstract data types, by having a concrete state machine with concrete states and a concrete set of transitions. And we need to define an initial process expression that if, say, we have 5 state machines, that we have 5 state machine processes, which are all past this concrete instantiation of the state machine data object. And if you would like to check this out, if you would like to play with it yourself, you can also find the model on GitHub. So the FORTE paper has a link to the GitHub. All right, this is the main content of our paper, but I'd like to talk a bit more about steps we've taken after submitting the paper. We've been working on an automated translation tool, so it's still quite a bit of work to write instantiation yourself, so that can be done better by using an automated translation tool that takes as input state machine diagrams and internal block diagrams. And this tool combines these internal block diagrams and extracts all the port connections. It performs a number of consistency checks, so both internal consistency of each diagram and the consistency between the diagrams. And it spits out a configured mCRL2 model using this generic model. So a bit about our experience of formalizing directly in mCRL2 compared to using pen and paper and writing down structural operational semantics of state machines. So I'd say the biggest benefit is that we have a pretty small gap between writing down the semantics, formalizing, and having an implementation of an automated translation. Because once you have the formalization, you only need to kind of produce the instantiation. So you're already pretty good on the way to say it like that. Other benefits of using kind of a tool that kind of acts like an IDE is that it forces you to be very precise. In fact, you're by definition working in a formal manner. And you have a parser that gives you quick feedback. So if you make a small typo and or the types don't match in operations, then the parser will point you towards the error. It also has some drawbacks, this way of working. It can be difficult to debug data equations. So if you define an operation that filters the number of transitions, checks whether they are enabled, and it is technically correct in the sense that the parser doesn't give any error, but it simply doesn't do what you want. It also includes transitions that are not enabled. Then it can be a bit difficult to find out what is going wrong, because in the end mCRL2 isn't a fully fledged IDE with IDE debugging support. And mCRL2 is also not very well suited to check and report on consistency problems. But our solution is to do this in the pre-processing step. We've also applied our translation framework on a specific Ulinx interface. So we've obtained an mCRL2 model of the level crossing interface. Initially, the state space was 2.8 billion states, which is pretty big. But we were able to do some optimizations of our formalization so that we can kind of combine some separate steps in the run to completion of these state machines. So we used to have that you first select the transition and then you execute some behavior and then you send the message on a port. And by slightly changing the semantics and combining some of these steps into one step, we can reduce the state space to around 100 million. And that is small enough that we can work with it using the mCRL2 toolkit. So we've been able to verify some basic safety requirements. And we are still in the process of interviewing engineers from DB and ProRail to get more safety requirements that we can verify for this model. Some future work. So in the end, the idea of Formalisation is to apply formal methods for all interfaces of Ulinx. So to be able to do this, we must measure the scalability and probably we also need to improve it. So this level crossing interface is a relatively simple interface consisting of only 6 components, and there are Ulinx interfaces that are much more complex. So we will likely need to find some tricks to be able to deal with these. One of the reviewers of our FORTE paper pointed us to the precise semantics of UML state machines. So this is a document by the OMG organization, which is the same organization that brings out the UML and SysML specifications. Our semantics is not fully in line with precise semantics of UML state machines, and we are doubting whether to adopt it in the Formalisation project. Since in Ulinx we already define all the semantics ourselves, we include it in the Ulinx standard. So it might not be that necessary, but we do think it is a very valuable to make a version of our model that is in line with this precise semantics of UML state machines, and also to help the broader community of people working with state machines. That was my talk. Thank you for listening. I welcome any questions you may have.